Hello, my name is Elda Arevalo, and together with my advisors, Dr. Edith Arielia Gutierrez Segura, Dr. Ivan Garcia Orozco, and Dr. Marcos Jose Solache Rios, we developed the work entitled Montmorillonite Clay Modified with Zinc Oxide Nanoparticles for the removal of indigo carmine and methylene blue dyes. Summary. The global water situation represents a critical issue worldwide. UNESCO forecasts that by 2050, due to rapid population growth, climate change, and the overexploitation of water resources, between 1.7 and 2.4 billion people in urban areas will face water scarcity. It is estimated that between 10% and 15% of synthetic dyes used in industrial processes are not fixed to the substrate and end up being discharged into natural effluents. This accounts for up to 280,000 tons of dyes per year, significantly affecting water quality in regions with high textile and industrial activity. Dye-contaminated effluents may contain concentrations ranging from 600 to 800 milligrams per liter, reducing water transparency, inhibiting aquatic photosynthesis, and harming microbial life. These pollutants often require advanced treatment methods for effective removal. In this study, Montmorillonite clay was modified with zinc oxide nanoparticles, ZnO, to remove indigo carmine, IC, and methylene blue, MB, two dyes that appear visually similar but possess significantly different properties. The synthesis procedure of the composite was as follows. The zinc oxide nanoparticle Montmorillonite clay composite was prepared by chemical precipitation. The Montmorillonite clay was placed in contact for 20 minutes with 50 milliliters of a 0.5 molar per liter sodium hydroxide solution, followed by the dropwise addition, approximately 0.5 milliliters per minute, of 50 milliliters of a 0.5 molar per liter zinc acetate solution. The mixture was stirred for 3 hours at 60 degrees Celsius. The precipitate was centrifuged at 6,000 revolutions per minute for 5 minutes and washed 4 times with deionized water and ethanol in a 3-to-1 ratio. It was then dried at 100 degrees Celsius for 15 hours and calcined at 400 degrees Celsius for 3 hours to obtain the zinc oxide nanoparticle Montmorillonite clay composite, ZnO. The composite was characterized by elemental analysis using energy dispersive X-ray spectroscopy, EDS, with a DX4 Zonda scanning electron microscope. The table shows the composition in weight percent and atomic percent for the Montmorillonite clay, MC, and the ZnO composite before contact with the dyes. The analysis of the ZnO sample revealed significant changes in the chemical composition of the solid after treatment with sodium hydroxide and zinc acetate, followed by calcination at 400 degrees Celsius. Firstly, the complete removal of sodium and calcium cations originally present in the Montmorillonite clay was observed, indicating that both were effectively washed out and were not structurally incorporated into the material. This is consistent with the high solubility and weak interaction of these ions with the clay matrix. In contrast, a marked increase in zinc content was recorded, reaching 40.52 weight percent, confirming the incorporation of the metal cation into the solid, presumably as dispersed or supported zinc oxide on the clay. Finally, a carbon content of 4.67 weight percent was detected, attributable to carbonaceous residues from incomplete decomposition of the organic acetate. These results demonstrate the successful modification of the material's composition, with selective removal of exchangeable cations and enrichment in zinc as the active phase. Adsorption experiments. In the adsorption experiments, isotherms were obtained by contacting 10 milligrams of the ZnO material with 10 milliliters of each dye at initial concentrations of 1, 5, 10, 20, 30, 50, 100, 200, 300, and 400 milligrams per liter, and the mixtures were stirred for 48 hours. For the adsorption kinetics, the following contact times rise: 5 minutes, 10 minutes, 15 minutes, 30 minutes, 1 hour, 2 hours, 3 hours, 5 hours, 8 hours, 16 hours, and 24 hours. In both experiments, phases were separated by centrifugation at 6,000 revolutions per minute for 10 minutes, and dye concentrations were determined by UV-Vis spectrophotometry using a Genesis 10S UV-Vis spectrophotometer. The adsorption models used to fit the experimental isotherm data are the following: model of Langmuir, model of Freundlich, and model of Langmuir-Freundlich. OSIPS model, where QE equals amount of dye adsorbed at equilibrium, CE equals concentration of dye in solution at equilibrium, QM equals maximum adsorption capacity, KL equals Langmuir isotherm constant, KF equals Freundlich adsorption capacity constant. 1 divided by N equals Freundlich adsorption intensity, or heterogeneity index, dimensionless. It indicates whether adsorption is linear when 1 divided by N equals 1, favorable when 1 over N is less than 1, or unfavorable or very weak when 1 over N is greater than 1. KS Masser SIPS affinity constant. 1 over N sub S equals SIPS adsorption intensity, or heterogeneity index, dimensionless, indicates whether the model reduces to the Langmuir isotherm. When 1 over N sub S equals 1, whether the surface is heterogeneous, when 1 over N sub S is less than 1, or whether adsorption is favorable at high affinity sites, when 1 over N sub S is greater than 1. The experimental data for the adsorption kinetics were fitted to the following models: pseudo-first-order model, pseudo-second-order model, and second-order model, or Ilovich model, where QE equals adsorption capacity at equilibrium, K1 equals pseudo-first-order adsorption constant θ equals time in hours, QT equals amount of adsorbate retained at time t alpha equals second-order adsorption constant, beta equals second-order desorption constant, K2 equals pseudo-second-order adsorption constant. And finally, we calculate the thermodynamic parameters, such as enthalpy change, entropy change, and Gibbs free energy, for the adsorption of indigo carmine and methylene blue by the MC nan ZnO, were calculated by the Van't Hoff equation and experimental data, where K equals equilibrium constant. The Kx is value of the kinetic model, constant that best fits the experimental data. Delta H equals adsorption, enthalpy. Delta S equals adsorption entropy. Delta G equals Gibbs free energy. R equals universal gas. Constant Kb equals Boltzmann. Constant H equals Planck. Constant T equals absolute temperature. M equals slope that accompanies 1 over T. For indigo carmine adsorption, experimental results showed a maximum saturation capacity of 58.42 milligrams per gram, with the best fit, R squared equals 0.92, to the Langmuir-Freundlich model, which predicts a theoretical maximum saturation of 84.5 milligrams per gram. This fit indicates a heterogeneous surface and possible monolayer adsorption with varying affinity. The kinetic data fitted best to the pseudo-second-order model with R squared equals 0.99, implying that adsorption is controlled by surface chemistry. That is, the rate depends on the number of available sites and solute concentration, involving chemical interactions. On the other hand, for methylene blue adsorption, experimental results showed a maximum saturation capacity of 82.81 milligrams per gram, with the best fit, R squared equals 0.96, to the Freundlich model, indicating a heterogeneous surface and possible multilayer adsorption with varying affinities and no clear saturation limit. Kinetic results for methylene blue adsorption suggest a chemisorption mechanism, since the pseudo-second-order model best fit the data with R squared equals 0.99. This model describes adsorption on heterogeneous surfaces with active sites having different energies. In the case of the thermodynamic parameter calculations, the changes in enthalpy, entropy, and Gibbs free energy were determined by plotting the inverse of the temperature in Kelvin against the natural logarithm of the pseudo-second-order rate constant K sub 2, and fitting a linear model to obtain a Van't Hoff type equation. The results for indigo carmine show that the value of delta H is greater than 0, indicating an endothermic adsorption process that is favored by increasing temperature. In the case of delta S, the negative value indicates that the system becomes more ordered during adsorption. This suggests that not all available adsorption sites behave the same way, and that the surface exhibits varying affinities for the adsorbate. Meanwhile, the positive values of delta G indicate that the process is not spontaneous within the temperature range of 25 to 45 degrees Celsius. For the methylene blue analysis, the same conclusions were obtained regarding the signs of the thermodynamic parameters. In conclusion, adsorption isotherm results showed that the composite material exhibited a maximum experimental adsorption capacity of 58.42 mg per gram for indigo carmine and 82.81 mg per gram for methylene blue. Additionally, adsorption kinetics were studied at different temperatures, allowing the calculation of thermodynamic parameters such as enthalpy change, entropy change, and Gibbs free energy change. The results for indigo carmine and methylene blue adsorption suggest a chemisorption mechanism, as the pseudo-second-order model provided the best fit at 25, 35, and 45 degrees Celsius. R squared equals 0.96 to 0.99. The thermodynamic parameters indicated an endothermic adsorption process favored by increasing temperature. Furthermore, the system becomes more ordered during adsorption, suggesting that not all adsorption sites behave identically, and that the surface exhibits varying affinities for the adsorbate. Thanks for watching the video.